Welcome to lecture 11. Last time we introduced unit 3 in the sense that we started talking about work. We're going to review what we discussed last time and then make the connection that I was referring to between work and energy. So to recap, last time we discussed that work is going to be quantified by this scalar product that you see here, where the force applied to an object is dotted with the displacement vector. That is force times distance times cosine theta, where theta is the angle between the force and the displacement vector. And this will give you the work that's been done. We discussed the units being joules, and we rewrote joules in a couple different ways based on the units that we have here, force and distance, and then also boiling that down to the fundamental units by replacing the units of newtons with kilogram times meter per second squared. Then we discussed the fact that although that this is a scalar quantity, so that it doesn't have directionality to it, it does have a sign that you have to pay attention to. Work can be positive or negative, that is. And so the limiting cases that we explored when we have theta equal to 0, where the angle between the force vector and the displacement vector is 0, then you have a positive one there multiplied by your force times your distance, so that you just have this, which is going to be greater than 0. If the force is pointing in the opposite direction from the displacement, so that this angle between them makes 180 degrees, then in that case we have work equal to minus force times distance, which is going to be less than 0. And if the force and displacement vector are at right angles to one another, then when we apply this equation, cosine of 90 degrees is equal to 0, so your work equals 0. Okay, and so in between these different values, between 0 and 90 degrees, we will have positive work, and between 90 degrees then and 180 degrees, we will have negative work. Then we did an example where we considered the various forces involved on a box that is sliding down an inclined plane, and we quantified the work being done by each of those forces in order to determine what the net work was on the box. Okay, so moving forward, I want to make that connection that I discussed before between work and energy. So energy can be thought of as the ability to do work, or another way to think about it is that when work is being done, then that's an indication that there's been a change of energy. So one of the ways that the energy can change is with respect to its motion. And what I mean by that is what we call kinetic energy. Kinetic energy is the energy that is associated with motion. You see here that it depends upon the velocity of your object. It also depends upon the mass of the object. So there is a theorem that connects the kinetic energy to the work directly, because if you think about what's happening, the kinetic energy of your object had to get from perhaps rest or some starting velocity to where it is now. And so work had to have been done. Or maybe it's in the process of being brought to rest, and so the velocity is changing in a different way, and so work had to have been done. A force had to be applied while displacement was taking place. And so the work energy theorem connects these two things and tells us that the work that's been done is equal to the change of kinetic energy. So there's a couple different things that could happen here. If your work is greater than 0, you might want to know then, is the particle speeding up, slowing down, or moving at a constant speed? Well, we can rule out the possibility that it's moving at a constant speed because the change of kinetic energy implies that so long as the mass is staying the same, there had to be some change of velocity. What about speeding up or slowing down? So for work to be less than 0, remember the vectors that we drew earlier, where if I have, say, a displacement vector pointed like this and the force pointed like this is the condition that is going to give me some work which is less than 0. So if you are being displaced, if you're the object being displaced, say, to the left, but the force is pointing to the right, then the force must be acting to slow you down. Okay, so according to this theorem, then, we can draw some conclusions here. If the kinetic energy is increasing, which we associate with speeding up, then the work is going to be positive. If the kinetic energy is decreasing, which we associate with slowing down, then the work is going to be negative. Anytime there's a constant speed, then the kinetic energy isn't changing at all, and so therefore you have work equal to 0. Okay, so let's re-explore the example that we discussed last time. Remember that we concluded that the net work that was done on this box was equal to 24.3 joules. So figuring out then what the kinetic energy change is for this box should be trivial, because through the work kinetic energy theorem, we have that work is going to equal the change of kinetic energy. Therefore, the kinetic energy change should also be this 24.3 joules. Knowing that kinetic energy change will allow us then to determine what the final speed of the box is going to be. So, plugging in the equation, remember that kinetic energy is 1/2 mv squared. So this change of kinetic energy appears like so. If the box was at rest to begin with, when we solve this equation, then this initial velocity goes to 0. And when we solve this equation, we get that the velocity, the final velocity, is going to be equal to the square root of 2 times the work done over the mass. When we plug in the numbers that were given in the problem, we can then determine that the final speed of the box is going to be 4 meters per second. Okay, so I want to pose another question, however. What if during the course of the displacement of your object, the force that's being applied is not constant? Perhaps you push a lot and then a little and then even less, or maybe the reverse. So in order to figure out what the net work would be in this case, we would do something similar to what we did in the example and add up a little bit of work that's been done when you applied a certain amount of force plus different amount of work when you applied a different amount of force, and so on. And then we would get the sum total of the work that's been done. And if you can imagine making each of these little terms in our sum small enough to capture how the force varies over small distances of time, what does the sum really amount to? Effectively, it becomes an integral, where this is your infinitesimal distance that you've moved it, and this is the force that you applied over that distance, and then we're summing them up, i.e. integrating over the entire displacement. So anytime you have a force which varies in this sense, you're going to need to perform some sort of an integral. Now don't worry, we aren't actually going to need to do anything with this integral, but it's important to see how this all connects together. And it's important to note that the work-energy theorem is going to apply even if the force is not constant. But we do need to consider the line that the displacement takes place in. So let's think of an example of a force which isn't simply a constant value. And that would be our spring force. This is one of the forces that we did not yet cover when we were doing Newton's laws. We've covered the normal force, tension, friction, gravity, but we did not discuss the spring force. The spring force is not just some number, it depends upon how much you displace the spring. By the way, we don't necessarily need to even have a spring. A similar equation like this could apply to other stretchy things such as a bow and arrow. Okay, this particular equation you see here is often called Hooke's law. And it tells us that the more that we displace the spring, the more force is required. And there's some constant of proportionality, which we call the spring constant. And this is something that depends upon the material of the spring, and it might be something that is given to you or that you have to solve for. We can figure out what the units of the spring constant need to be, because we know that we want to have newtons in the end, right? Because this is a force. So a newton is a kilogram times a meter per second squared. That's what we have on the left-hand side of Hooke's law. On the right-hand side of Hooke's law, so far, we've just got a meter. So what did the units have to be for the spring constant? Well, they've got to be a kilogram per second squared. Okay, that's your spring constant units. Or another way to look at it is a newton per meter. Because when I multiply that by the meter, then I will get back newtons. Okay, so although this spring force is not constant, it's something that's easily integrable. For those of you who have progressed to this point in calculus, you may be able to perform this integral on your own. If not, that's okay too. You can take my word for it that what we get out of this is the following. Okay, and oftentimes then this is rewritten as 1/2 k x initial squared minus x final squared. Okay, so why don't we do an example where we use the spring force and we examine the relationship between that force and the work that was done. So one common application that uses a spring is a pinball machine. When you pull back on the plunger, you are compressing a spring, which will then allow the ball to fly and actually do the pinball game. So we want to know how much work is being done based upon the spring constant that we were given and the displacement that happens as well. Okay, in order to figure that out, we can go ahead and, we want to know both the force and how much work is done, so we can go ahead and do the first of these things first using Hooke's law. And this is a basic plug and chug thing. We're just going to multiply 0.06 times 100, so we will get -6 newtons. To compute the work, this is also relatively straightforward. We will use this equation that we derived on the previous slide, and plugging in the values there, we get -1/2 k times 0.036 meters squared minus 0. that will give me 0.18 joules. Okay, now we want to connect the work that's been done. I'm going to rewrite it here. Work was equal to 0.18 joules. And we want to figure out, based upon that work, how fast the ball will now be traveling when this child lets go of the plunger. Well, remember through the work kinetic energy theorem that work is going to equal our change of kinetic energy. And since the ball was at rest to start with, this will just equal 1/2 mv final squared, which is what we want. We want to know what v final is. Okay, just the same way we solved for this in the previous example, you will end up with this equation, which if I plug in the mass of the pinball, I will find a speed of 2.1 meters per second. Okay, so that's an example of how we can think about the force and how it relates to the work, and then how that also relates to the kinetic energy. But I want to make a connection to another kind of energy. So in order to do that, let's review some things. We have certain forces that we've become familiar with that the work that's been done on, say, an object under the influence of that force does not actually depend upon the path that you take from point A to point B. And then we have other forces that we've worked with in the Newton's Law unit 2, which are going to depend upon the path that you take. So examples of these are gravity for the first case, friction for the second case. For gravity, it doesn't matter if I lift an object up or down 1,000,000 times, the amount of displacement is what matters, right? And so it didn't matter what path I took, the work involved is going to have to do with that displacement rather than the path that was taken. So that kind of force is what we would call conservative. On the other hand, the friction force, I would have to add up how much friction was going on here and here and here. And the longer my path is, the more net work I would have had to do. And so that's an example of what we would call a non-conservative force. Anytime I have a situation in which a force, the work that's being done is done by a force which is conservative, then this is associated with another kind of change of energy. And this property, or this type of energy, is what we would call potential energy. Notice that there is a minus sign in this equation here, but the work that's been done by this force is equal to the negative change of the object's potential energy. So the potential energy associated with the conservative force of gravity is what we would call gravitational potential energy. Typically, we indicate potential energy with some sort of U and perhaps a subscript. But we can see in this equation, which quantifies gravitational potential energy, we can see the force and we can see the distance. And so this equation tells us that the more that something weighs, the more potential energy it's going to have. Also, the higher the object, the more potential energy it's going to have. This is why when I found myself at the top of this mountain after having climbed it, I felt a little bit vertigo, right? I had a lot of potential energy and I knew it. I was at a very great height. And so when you have that kind of potential energy, you can think about the fact that it has the potential to do something, to do work. Once I started climbing back down, belaying back down, you can see that my height is decreased and my potential energy is likewise decreased. This is the same reason that it's wise to put something heavy like a cast iron skillet on a low shelf rather than a high shelf. It has the potential to do a lot more damage if it's on a higher shelf. Okay, another kind of potential energy associated with the other force that we were just discussing, which is conservative, the spring force, is what we would call elastic potential energy. Remember that it doesn't necessarily have to be a spring involved. It could be something like a bow and arrow. And when you stretch that elastic or that spring a certain distance x, then the potential energy associated with that is 1/2 kx squared. Okay, so I've basically told you that if you have only conservative forces acting on a system, then we have this property that the work that's done by those forces equals the negative change of potential energy. But earlier I had told you that when you have net work being done, that's associated with a change of kinetic energy, according to the work energy theorem. Well, if this is equal to the net work that is done, and so is this, then they must equal one another. Change of kinetic energy must equal the negative change of potential energy anytime I have only conservative forces working. Rearranging that, I can arrive at this equation right here. Now, kinetic energy combined with potential energy makes up a quantity we call mechanical energy. And so this equation in the red box tells us then that if there are only conservative forces acting on the system, then the change of mechanical energy must be equal to 0. In other words, if I add up the kinetic energy and the potential energy in the initial state, it has to equal the kinetic energy and the potential energy in the final state. They each independently could change, but the sum total of the two has to remain the same. And with this, we have derived the first of our conservation laws, the conservation of mechanical energy. And we will explore that law more in the next lecture. Thank you.